Single stage transistor amplifier. In a single stage transistor amplifier, only one transistor and its associated circuitry are used. For a practical transistor amplifier, it consists of biasing circuit R1, R2, etc. The input capacitor is used to couple the signal to the base of the transistor. If it is not used, the signal source resistance will come across R2 and thus change the bias. The capacitor Cin allows only AC signal to flow but isolate the signal source from R2. Emitter bypass capacitor CE is used in parallel with the emitter resistance RE, which provides a low reactance path to the amplified AC signal. If we have not used CE, then amplified AC signal flowing through RE will cause a voltage drop across it, thereby reduce the output voltage. A coupling capacitor CC, which used to couple one stage of the amplifier with the next stage. If it is not used, the bias condition of the next stage will be drastically changed due to the shunting effect of the collector resistor RC. This is because this RC will become parallel to the upper resistance R1 of the next stage. In a amplifier there is AC component and a DC component. So base current will be a mixture of base IB, that is DC current, and AC current. We will represent as small I capital B. Similarly, collector current is capital IC plus small ic, that is small I capital C. So this emitter current is I is equal to IE plus I capital E. Here I have given an input signal. The output is like this. In the positive half cycle of the input signal, the current increases, the base current increases. Since the base current increases, the collector current also increases because IC is beta IB. But since the collector current increases, the voltage drop across RC also increases, that is ICRC increases. Since ICRC increases and VCC is a constant, the output voltage VCE decreases. Or in other way, I can say when the input signal increases in the positive half cycle, the output signal increases in the negative way, or the input voltage and output voltage have a phase difference of 180 degree. We can prove it mathematically also. So the total instantaneous output voltage VC is VCC minus ICRC. If you differentiate dVC is equal to VC is a constant, 0 minus dICRC. Change in VC is equal to change in IC into RC with a minus. This minus gives the output voltage is 180 degree out of phase with the input signal, or the phase difference of 180 degree between the signal voltage and output voltage in a common emitter amplifier is known as phase reversal. So in a common emitter amplifier, there is a phase reversal of 180 degree between input voltage and output voltage. You can prove it graphically. So this is the VC IC graph. Here AB is the load line. Base current varies about 10 microampere, that is a maximum of this one plus 5 and a minimum of minus 5, that is IB maximum is 15 microampere and minimum is 5 microampere. IB is maximum, see the point G, VC is minimum. When IB is minimum, this value graphically it is clear, VC is maximum. That's the idea. When IB is maximum, VC is minimum. When IB is minimum, VC is maximum. So it is very clear that these two are to have a phase difference of 180 degree. This is a circuit and all I have given here. Q value 10 microampere. It changes 50 microampere and 5 microampere. The beta value is 100. 10 into 100 microampere is equal to 1 milliampere, that is the IC. 15 into 100 microampere, that is 1.5 milliampere, and similarly 0.5 milliampere. This is the output current. So let us calculate the output voltage. The output voltage VC is equal to VCC minus ICRC. When IB is equal to 10 microampere, then IC is equal to 1 milliampere, beta IB. Therefore VC is equal to 10 minus 1 into 4. 4K is the RC. that is 6 volt. So this is the base 6 volt. Similarly, when IB is equal to 15 microampere, VC is equal to 4 volt. This is the minimum. So this is when 15 microampere minimum. When IB is equal to 5 microampere, VC is equal to 8 volt maximum. So mathematically also it is very clear. There is a phase difference between input voltage and output voltage. See, the input current and output current have no phase difference. They are in phase. In a transistor amplifier, there is both DC and AC conditions. The DC source set up DC currents and voltage, whereas the AC source produces fluctuation in transistor current and voltage. To analyze the action of the transistor, it is better to split into two parts. One is for AC analysis and the other is for DC analysis. Okay, this is a circuit. Here there is both DC and AC stages exist. First we are going to make a DC analysis. For that we must have a DC equivalent circuit. So in order to get a DC equivalent circuit, first reduce all AC sources to 0 and open all the capacitors. Okay. First reduce all AC source to 0. So make signal 0 and open all capacitors. So it will look like this. VCC, there is no source, no capacitors. Okay, there is no capacitors. So this is called the DC equivalent circuit. Similarly, for an AC equivalent circuit, reduce all DC sources to 0, that is VCC 0, and short all capacitors. Okay, not remove, short all capacitors. This is the AC equivalent circuit of this amplifying circuit. Load line analysis. First, DC load line. So this is the circuit. So this is equivalent DC equivalent circuit. We have VC is equal to VCC minus IC into RC plus RE, where I have choose IC is approximately equal to IE. Therefore, this is the DC load line. And this is VCC and VCC by RC plus RE. AB is the load line. Q is the Q point. Zero signal point. VC is maximum when IC is 0, that is VCC, this point, and maximum value of IC is when VC is 0, that is VCC by RC plus RE, that is this point. These 2 points constitute to the DC load line. An AC load line, the line on the output characteristic of a transistor circuit which gives the value of IC and VCE when signal is applied. This is the AC equivalent circuit and this is the AC load line. Maximum value of VCE is VCE DC value plus IC or AC, and maximum value of on IC is equal to capital IC plus VCE by RAC, where RAC is RC parallel RL, that is RC RL by RC plus